A little more on coordinate systems and making measurements. Okay, so the Earth's true shape is a geoid, and exaggerated, it looks like this. Now, how do we measure this? So it's a measured surface. So one thing we could do is we could use a gravimeter, and this is sort of something you could do on Earth. Basically, the idea here is that the mass that's hanging out here will be pulled by gravity, and if gravity is stronger, it will change the angle. So when you measure the surface, the important thing to recognize is that we're really measuring values of gravity. So on a satellite, we could do this as we orbit it around from this characteristic, and we can measure the height h. Again, we're looking for a surface of kind of constant gravity. And if you notice on this particular drawing, it's interesting is that the geoid wanders around, but yet the surface of the sea wanders around as well. So sea level is really not level with respect to that. In fact, the sea level is a meter or so higher over the geoid off the coast of England than it is off the coast of the United States. So a very sensitive project that was produced by NASA back in 2002. It's called the GRACE project. And essentially what was done was they launched two identical satellites. And these two satellites communicate back and forth with each other. And essentially their primary goal is to measure the distance they are apart. Well, when this satellite, the lead satellite, goes over a section of the Earth that has a higher gravitational pull, it will pull this satellite down a little bit and cause it to speed up, much like it would occur if you were a skater and you were starting a spin. As you bring your arms in, your spin is faster. So if we bring this satellite closer to the Earth, it's going to speed up. And when it speeds up, it gets further away from the satellite behind it. But then, as the trailing satellite goes over the same aspect, it will speed up as well. So now what happens is that as you go around the Earth, these two satellites are getting closer together or further apart, depending on who's over the heavier part of the Earth. And kind of from a strange characteristic that these satellites at 137 miles up are able to measure a resolution of the geoid down to centimeters on the surface of the Earth. So we have all these different references. We have the ellipsoid. So we pick an ellipsoid that best fits our continent. And then we have, so this would be described as North American datum in 1983. And then we have a geoid that represents from that North American vertical datum of 1988. And so that gives us a height in here. And then we can further refine this by using a geoid height, the GEOID 03, which would be from the GRACE project. So all of this is necessary to establish what we are really interested in is what is your elevation. So your elevation is your reference from the geoid to the topographical surface. Okay, so if we have, let's say we have high density rocks here, which would give us a higher level of gravity, and low density rocks there. So this would be the strata of the Earth's crust, not just a few rocks laying on the surface. So here we have the sea level, the ocean, and so as we kind of work through here, what we are establishing is level surfaces. In other words, even though this surface is curved, if we were to take a pool of a glass of water, it would be level here and it would be level there. So these level surfaces are surfaces with constant gravity. And you can see that this constant gravity would be pulled a little closer to the center of the Earth here because there's more mass in the earth in the crust at this point than there is out here. So we define the geoid as one of these levels. You know, somebody pick one, and so that's what was done. So now you have these surfaces of constant gravity above and below that particular scenario. What's kind of strange is that if you were to take a plumb line and go from one level to the other, you would find that the plumb line wouldn't hang straight down towards the center of the earth, but the plumb line would actually hang from here to here, would be at this angle and that angle and this angle. It's just greatly exaggerated, of course, but you get the idea. Is that it doesn't get pulled straight down. It gets pulled perpendicular to these surfaces of constant gravity. Okay, so some description, elaborate on those. I'll let you read those at your own time. So how does GRACE compare to the North American vertical datum of 88? So how does O2 compare to 88? How does that work? And light white here, you can see the United States, and over here is the difference in meters between the two. So the North American vertical datum of 88 was off, was too high here, was too low there. So it gives you an idea. These are in meters, so we are very, very interested in having very accurate representation to spend the kind of money we did to launch satellites to get from GRACE to the North American vertical datum. So the geoid, if looking at the United States a little closer, just for sort of some interest points, you can kind of see some features, but there are some features that don't make much sense, like what's this ridge running down through here, and what's this big trough running down through what looks to be around New York or the New Hampshire and Vermont. And so what this does is the geoid gives us an idea of what's happening deep inside the Earth, underneath us. Off the coast of East, there's a big depression here, and this depression, which has caused the geoid to essentially be pushed in, was due to the Ice Age. So slowly that will that'll come back as the Earth adjusts. So all this stuff about the geoids and the reference surfaces relate to data. And so if we have data that was acquired in 1835, for example, then obviously it could not have been taken with respect to any of these datums or ellipsoids. So depending on when our data was acquired, how that data is represented, it relates to essentially the year, what the possibilities are. For example, we probably are not going to find anything in the United States that used this particular, Australian ellipsoid. That makes no sense, right? So the ellipsoids and where your data comes from is important as we move around, because we may want to use some really old data. And we may have to shift things and map from one surface to another. Now, fortunately, we don't have to do this as an operator anymore. This is going to all be done by the software. The software grabs the metadata and automatically to do this for us. So our position horizontally, latitude, longitude, and altitude. Heights are measured with respect to the geoid. And we have this kind of repeated slide here that shows you the spheroidal height, the orthometric height. This is the height to the geoid. Bottom line, the transformation isn't perfect. And what can happen to us when we build maps is that what we bring into the map first may determine the look of the map. So What you want to be careful with is if you bring in data 1, 2, 3, 4, and it doesn't look well, just start over and bring in data 4, 3, 2, 1. So how you bring your map in determine or how your data into your map determines the transformation process. And so you can play around with this a little bit, or you can make modifications. The closer data that you get, I call it closer because it's like zooming in. So if we have data that relates to the roads that are in the Chemung County, which is in New York, if we bring in that data first, it's probably going to be better than if we bring in the roads of New York first and then the roads of the Chemung County. So depending on how you go, it works. You probably want to bring in newer data first and then the older data